Okay, so today, Aman, I will be teaching you about geometric series. So what is a geometric series? Geometric series is a series where each term is multiplied by some common ratio. And the previous term times the common ratio will be the next term. So the common form of geometric series is this. The first term times the common ratio to the power of n. That's our common form of geometric series. Got that? Alright. So we can also write this as x of 1, and onwards what we did is of 1 r again. Now to find the sum of the series, we can say, well, this is equal to this. If we multiply both sides by r, we get sum of 1 r squared, base of 1 r cubed, base of 1 r to the fourth, onwards till we get a sub 1 r to the n plus 1. That's s times r. Now if we subtract this equation from this, we also notice that each one is just multiplied by r, which is what I did. So if we subtract this bottom equation from the top equation, we see that this and this cancel out, and it will continue at this pattern, except for the very last term here and the very first term here. So we'll have a sub 1 minus a sub 1 r to the n plus 1 equals s times 1 minus r. And that just came from s minus sr and then factoring out the sum. So then if we rewrite this, we can say the sum is equal to a sub 1 times 1 minus r plus 1 over 1 minus r. Well, we know that in a geometric series, for it to converge and for it to actually reach a sum, we know that the common ratio, the absolute value of the common ratio, has to be less than 1. So if r is less than 1, or if the absolute value of r is less than 1, that means it's a fraction. And this is as n approaches infinity, we know that a fraction to the power of infinity goes to 0. So we can say that this term goes to 0 at n equals infinity. So we can say that the sum of a geometric series is the first term over 1 minus the common ratio. So also in geometric series, there's the concept of the interval of convergence, which is basically the interval with which the sum of the series converges to a single number. So we told you that r, or in the equation s equals a sub 1 over 1 minus r, the absolute value of r has to be less than 1. So if in one case that r, let's say, was not equal to x, let's say r was equal to maybe x minus 2, and a sub 1 was equal to like 15. So what would be the interval of convergence for this kind of example? So we would say that the sum is equal to 15 over 1 minus x minus 2. Well, whenever we need to find the interval of convergence, the a sub 1, the first term, doesn't matter. All that matters is the common ratio. And we know that this common ratio, absolute value of that has to be less than 1. So the interval of convergence is basically taking this, the absolute value of x minus 2 is less than 1, which is pretty much it. Another example would be, let's say, if we had the common ratio, or let's say we were given the equation, the sum is equal to 1 over 3 minus x. Well, we know that we need to get the equation in this form. So in order to get that form, we need to first factor out a 3. So we have s equals 1 over 3 times the quantity 1 minus x over 3. Well, we can also say that this is 1/3 over 1 minus x over 3. That gives us the same format of the equation over here, and we can now say that x over 3 is the common ratio. So the interval of convergence is the absolute value of x over 3 is less than 1, so the absolute value of x has to be less than 3. Hey, come on, do you understand? No? What don't you understand? this. Alright, would you like an example?
Yes.
Okay, so first you're going to tell me if this series converges or diverges, okay? If the sum of the series converges or diverges. So let's say we have the first term be equal to 23 and the common ratio be equal to 3/4. First tell me, does it converge or does it diverge?
Not enough information.
Huh? That is wrong. We do have enough information. Remember, the only thing that we need for the sum of a series to converge is that the common ratio is less than 1. So we see here, the common ratio is 3/4. So the sum will converge. So how do we find the sum of this series?
A1 over 1 minus R.
Yes, this equation of mine. Good job. So the sum of the series, A1, the first term is 20, over 1 minus R. That gives you
24 times 4.
92.
23 times 4.
Good. 92. Okay, next is an example. If we had a sub 1 equals to 10 and R equal to -4/3. Come on. Does this converge or the sum of the series converge or diverge?
Diverge. Because
Why?
R, the absolute value of R is supposed to be less than or equal to 1. But in that case, the absolute value of that is equal to 4/3, which is greater than 1.
Good job. So there is no sum for this series. Okay, so the other topic we have is power series. A power series is basically a more general form of the geometric series that we know. So we know that the general form of a geometric series is a sub 1 times the common ratio to n equals 0 and 3. So a power series, on the other hand, the general form is this. Infinity a sub 1 times x minus c to the n. Okay, so in this case we see that the common ratio, or so to say common ratio because geometric is a more specific form of this, the common ratio is x minus c. So in this case, all we have to say for the interval of convergence is that the absolute value of x minus c is less than r, which is the radius of convergence, which will vary for the specific power series that we're doing. So one example we could have is to express some equation as a power series. So if we have the equation f of x equals the natural log of 1 minus 2x, we can try and express this as a power series. Well, we know from our common maclaurin series that 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus ... onwards. And so we know we can just plug in 2x for this, but to get to that form of natural log, we would take the integral of both sides. So negative ln of 1 minus x is equal to x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4 onwards. And so then what we do is we know that the form of this, or we can find that the form of this for the series is just 2x to the n over n. And then since we have the negative here, we put the negative over here, which will be carried through. And we got 2x here because we wanted the natural log of 1 minus 2x. And if we had just 1 minus x, that would just be this. This is the series form of the equation we got by taking the integral of the simple form of 1 over 1 minus x. So to make this into the equation that we were given, we just plug in 2x for x, which is why we had the 2 here.
Okay, so today, we're going to be learning about Taylor series. And so I just wrote this out to speed up the process a little bit so it doesn't take as long, but whatever. So we're going to look at the equation f of x equals x to the 4th. And so this is a general equation for that given polynomial. And we're going to try to represent this polynomial using the series. Okay, so if you write it out here, it's just generally like that, where you're plugging in n for each term. And then when you expand it from this step to this step, you're just expanding. And from there, we're going to color code and look for all the common terms. So we're going to first start with constants. So Aman, what are our constants?
would be that, and then that, and then that,
Which one?
that. You know
That.
That.
That?
That.
Yeah.
That. Yes,
No.
that. Yeah.
Yeah.
Yeah. And then that. And then that one.
Good job. Very good.
Thank you. Thank you.
Alright, so we're just gonna write them out to organize them.
You could go and sit back there and study complete solutions. I don't want to count this as a third job.
Okay, so now we're gonna look at the x terms and see if we can find them. We're gonna use red. X terms. Okay, so here's one, here's another, and another.
And that one.
Good job. Yay! Okay, and you can start to notice that each of the terms that we're looking at is one before the one we had already put.
They don't see her. It's multiple choice. Yeah, I have to check the work.
Minus 4a 4x each.
Okay, and now use blue.
Blue.
You don't want to put two blues. Okay. X. We're gonna do x squared now. X squared terms.
So we decide.
And so here's one.
Minus 2a cubed x.
Good work.
And then that one.
Good work. Okay. So then we write it out like that. Okay. Now we're gonna look for the x cubed terms. Please put your phone away, class. Okay, fine. That's okay. Okay, now we're gonna look for the x cubed terms. And it gets pretty easy once you start seeing the pattern.
Well, there's only parametrics and polars on the board.
Just a side note, when you are expanding this, it's probably a lot easier to use Pascal's prime to do the bigger ones, so you don't have to. And then finally, we're gonna look for the x to the fourth term. And that is just this one. So we know that looking back at our equation, we know that f of x equals x to the fourth, so this whole thing has to equal x to the fourth. So we know that this variable is x to the fourth, so we know x to the fourth equals x to the fourth. And by knowing that everything adds up to x to the fourth, and we already have x to the fourth, what does this make the rest of these? It makes it 0. Because if you have your given value, and you add something to it, but you only want to get your given value, it has to add 0. So these all equal 0. Do you understand?
Yes.
Okay. Okay, so if we know that a sub 4 x to the 4th equals x to the 4th, then we know that a sub 4 equals 1. So we can write that in, a sub 4 equals 1. And we can use that to find a sub 3. So if you plug it in, you know that a sub 4 equals 1, so you can just mark that out. And if you factor out the x cubes, then you know that that also equals 0, so we can factor those out. And then you bring that over to the other side, and you get a sub 3 equals 4c. C. Okay. And then we can again use a sub Do you have a question?
Yes.
What's your question?
Why is a sub 4 equal to 1?
Because you have your x to the fourth variable, and you know from your given equation x to the fourth equals x to the fourth, then if you divide x to the fourth by x to the fourth is equal.
1.
Yeah!
Eureka!
Very good. Okay. So continuing on. We can continue to substitute in each of the a sub 3 and a sub 2 once we find that. So this equals 1. We can again cross out all the x squareds. We factor that out equals 0. And then you get negative 12 c squared for that. And then so you know that a, and then this is 6c squared. So when you pull this over to the other side, you know that a2 equals 6c squared. Okay, and keep going on until you finally get up to your a sub 0. If you finally, if you look at all these given values, you can see that there is a relationship between all of these. So you have c to the fourth, and then you know that the derivative of c to the fourth is 4c to the third. And then if you take the derivative of this is 12c to the c squared. But if you divide that by the factorial that it's given up here, then you have this value, and then you keep dividing it by the given value, the c, and then also by the factorial. Okay, so let's do that. So this is f of c. Looking back at this x to the fourth, this is f prime of c over 1 factorial. This is f double prime of c over 2 factorial. This is f triple prime of c over 3 factorial. And finally, this is f quadruple prime of c over 4 factorial. Okay. So, once you have these, you know that a sub 0 equals f of c. So you can plug that back into this original equation. So you finally get that whole equation, and then you can see from that, finally get your general equation. You get n equals 0, this, f to the n of c, x minus c. C is your center point, over n factorial. And then that's your general equation.
Wait.
Solid. Okay, so now we're going to do a Taylor example, and it's actually going to be an AP problem. So it says, let f be the function given by f of x equals 6e to the negative x over 3 for all x. So A says, find the first 4 non-zero terms and the general term for the Taylor series for f about x equals 0. So when it's x equals 0, like we said, it will just be a maclaurin series, so it's the same thing. So to start off, since you know it's maclaurin series and you know the given structure of maclaurin and Taylor series, we're just going to find the derivatives. And it says for the first 4, so we only have to find the first 3 derivatives, including this one. And so we know that this is e to the 6e to the negative x over 3. So we're actually going to factor out or we're going to just leave out the 6 for right now. And we'll multiply everything by 6 in the end. So we're going to have f prime 0, f double prime of 0, f triple prime of 0. Okay. So you know that this equals e to the negative x over 3. And at 0, anything e to the 0, anything to the 0 is just 1. Okay, and then so we multiply by 1/3, e to the negative. This goes to 0, so that's 1, so it's 1/3. Okay, and then you have negative 1/3 times negative 1/3. E to the negative. It's just 1/9. And then 1/9 times negative 1/3. E to the negative 1/27. Okay, fine. So those are your initial coefficients. And then once you have those, you can just plug it back into the equation. So we actually are going to multiply by 6 to factor the 6 back into the equation. So then you have 1 plus negative x over 3 plus x squared over 9 times 2 factorial. This is times 1 factorial if you remember, but it's just 1 so you don't have to worry about it. Minus 1 over, x to the third over 27 times 3 factorial. Okay, and then once you solve that out, you get 6 minus 2x plus, sorry, my nose is itchy, x squared over 3 minus x cubed over 27. Okay, yada yada, and that's just your first 4 terms, but it will go on if we were looking for all the other terms. So when looking for the general term, we have to consider a few things. We see that it's alternating, so we want to factor that in by saying negative 1 to the n. So that shows that it's alternating. And then we also want to factor in the 6, so we are going to multiply it by 6. And then we see that as every term increases, the x also increases. The x exponent increases, so we're going to do x to the n. All over, so we see here that the factorials are increasing, so it's n factorial. And then if you look here, it's 3 times 3 squared, and this is 3 cubed. So it's just 3 to the n. And so that's your general form and your entire steps to get to that. All right, so that's the answer for A. That's how you solve A. So B, we're going to work on now. So for B, it says, let G be the function given by G of X equals f of t dt. Okay. And it says, find the first 4 non-zero terms and the general term for the Taylor series for G about x equals 0. So it's the same as we were doing before, but we're just going to do the integral of the equation that we were given before, or that we found in A before. So it's 6 minus 2x plus x squared over 3 minus x cubed over 27. So we're just going to take the integral of that, and that looks something, like this. X squared plus x cubed over 9 minus x to the 4th over 108. And then when we're looking for the general term, we're just going to do the same things we did before, where we look, oh, sorry, I forgot the 6's. 6. Okay. We're going to look for the same exact things that we were looking for before. We are going to see that it's alternating, so we want to do negative 1 to the n, and then the 6. And then we see that it's, we see that there, we see that it's now not just x to the n, it's also x to the n, it's just x to the n plus 1, because this is a 0 term, and there is, so if it's x to the 0, then it's just 1. But if it's x to the 0, and then this equals x, so it's x to x plus 1, so it'd be x to the n plus 1. And so that would be your actual way to account for it. So you want to do x to the n plus 1. All over your factorials, and you saw that if you break this down, you see that it's n plus 1 factorial times 3 to the n, as we were doing before. All right, so that's how you solve part B. And so finally, for part C, for part C, it says the function h satisfies this equation. H of x equals k times f of x, f of ax, for all x, where a and k are constants. The Taylor series for h about x equals 0 is given by this. H of x equals 1 plus x squared, 2 factorial plus x cubed over 3 factorial, and so on, for x to the n over n factorial. Okay. And so it says find the values of a and k. And so for doing this, we want to kind of break it down to use these two equations to find a and k, and we want to look at it that way. So if we take the derivative of x, of f of x, we see that that equals negative 2e to the negative ax over 3. Because if we are just taking this, then we plug in, so our function then just becomes, so it's ax over 3 rather than just x over 3. So you get the derivative of your function, and then what we're also going to do is we're going to take a look at this h of x. And we know that this equation, h of x, we can recognize it as e to the x. Because if you break down e to the x in your in its Taylor polynomial, then it is, or Taylor series, sorry, then you can see that it represents this. So we recognize that, and then once we recognize that, we can plug h of x into it. So we see that h of x equals negative 2k e to the negative a x over 3. Okay, perfect. Sorry, that's an h. Okay, so once we find that, we can just, and we know that this is, so e to the x, and then we plug the h of x in for each other, and you get e to the x equals negative 2k e to the negative ax over 3. And then, as we solve it out, we see that a over 3 equals 1, and that negative 2k equals 1. Because we can divide, we can just do the algebra of that, which is simple. And then, so multiply by 3, divide by negative, so we get a equals negative 3, and divide by 2, multiply by negative, k equals negative 1/2. And so those are our values for a and k. So now we're going to take a look at maclaurin series, and the basic principle of maclaurin series, it's very, very similar to Taylor series. So Taylor series, you have this given equation of the sum of 0 to infinity of f of n times c over n factorial x minus c to the n. But so maclaurin, what he did is he wanted to find, instead of x minus c centered at a different point, he wanted to see it at 0. So for every single maclaurin series, c just equals 0. So you don't even have to include this x minus c because it's just going to be x every single time. Alright, so now we're going to go through some common maclaurin series. These are ones that you always want to look out for. If you find them on AP problems, it's very helpful to be able to recognize them quick. So the first maclaurin series is 1, oh my marker's running out, 1 over 1 minus x. And if you plug it into the maclaurin series and you do all the work, you get that it equals to 1 plus, sorry, my dog is barking, 1 plus x squared plus x cubed, and so on. And so after you find the common form, you get the sum in the interval 0 to infinity, x to the n, for all is less than 1. Alright, so that's your first one. And then your second one is just 1 over 1 plus x. And so after you do all the given all of the finding derivatives and of f of 0 and f prime of 0, f double prime, and whatnot, you find that the only difference is that 1 over 1 plus x makes it alternate. So you get 1 minus x plus x squared minus x cubed. So after you find the common series, you can easily find that the sum is, sorry, my dog is barking again, is equal to negative x to the n, to the n for all real x, all absolute values of x is less than 1. So next, e to the x. E to the x is one of the easiest to actually solve out because the derivative of e to the x is just e to the x. So after you solve that out, you find that it's very common used on AP problems, and it was actually used on the AP problem that we did. So it's helpful. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And so you go on and you find that the sum is equal to n equals from 0 to infinity of x to the n over n factorial. Sorry, my dogs are being crazy. And that is just for all real values of x. All real x. So that's just for all real x. Next, we are going to look at, we're just going to look at 3 more. We're going to look at sine x, cosine x, and ln 1 plus x. Because those are the most important. I just want to see what you think. Okay. Okay, so now we're going to look at sine x. And even though we just did it in the, sorry, the thing I'm throwing is my dog's toy. He's just wants attention, so he's been playing. Here, this is what he looks like. This is Fitz, and there's his toy, and he wants me to throw it. So there he is. And so that's why if you see me just throwing a random brown blob, that's what I'm doing. It's better than him barking. Okay, so we have sine x, and so as you saw in the other video, or either it's before or after, I haven't put it together yet, you see that after you divide everything out, you see the pattern, and so you see that it goes to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. And so you know that these are odd. Signs are the odd numbers. And so you know that your general form is just negative 1 to the n times n plus 1 over 2n plus 1 factorial. Fine. Okay, so actually I'm gonna do this out real quick because I think it's an important thing to be able to list out the factorial, and it's just a good example for finding a maclaurin series. So if you're gonna do this, you find f of 0, f prime of 0, f double prime of 0, and f triple prime of 0. Alright, and this is the same way you would find it for cosine as well. So you can apply this to both. So you know that f of 0 is sine of 0. And now f prime of 0 is cosine of 0. Shh, don't bark. This would be negative sine of 0. And that would be negative cosine of 0. Sorry, 0, not x. And so you know that this equals 0, 1, 0, negative 1. And so if you were to take the fourth derivative, you would find that it equals sine x. So it just goes in this 4 pattern. So it would just go back up here, and then it would go down, and then go back up and go down. So we're only going to go through 4. Okay, and so now, so you know that you have your f of 0, you have your maclaurin series guide. That's times x over 1 factorial 5. So you have that given guide. And so we're just going to plug it into that circumstance. So you have f of 0 is 0 plus f prime of 0 is 1 times x over 1 factorial plus 0 plus negative 1 times x cubed over 3 factorial. And so you're going to keep going on, and you would find that the next term would again be 0, and the next term would be x to the 5th over 5 factorial, and then it would just be x to the 7th over negative x to the 7th over 7 factorial. And so after you find that, you're to find the general term. 0, negative. Okay. Sorry, my dog's being annoying. So you're to find the general term. So you see that it's alternating, so we want to represent that. So we would find negative 1 to the n times, so this is the 0 term, this is the first term, second, so it's x, and so it's the first term, so we want to just do, as it says up here, x to n plus 1 over 2n plus 1 factorial. All right, so that is, and that's for all real x. Yeah, so that's for all real x there. And so that's just going through sine x. So when I go through cosine x, keep this in mind, and if you can, if you want to pause the video and try to find cosine x the way I found sine x here, and then double check it to see if the way you did it the other way, the way you did it the long way, to see if you can find like the maclaurin series for cosine. You can pause the video and do the same thing for cosine, or you could do it for ln of 1 plus x, or any of the other ones that I'm giving you. Okay, so cosine of x. All right, so that equals, so you knew that sine is odd, so it's really easy because cosine is not even. So you find that 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on, until you get your general form as just n equals 0, n equals 0, the sum from 0 to infinity of, so you want to represent that it's alternating, sorry, my marker is dying, times x to the 2n over 2n factorial. And so that is also for all real x. So that's your cosine function. I really hope you can see that. And then ln of 1 plus x. So this is our final one that you really have to keep in mind. And it is just, so after you solve it out, you get, so if you want to pause the video now, you should. And then you can see if you got it right. So it's x minus x squared over 2 plus x cubed over 3. And so you see that it's alternating, so you have to factor that fact in. And then you know that it's, sorry, and then I'm saying 1 minus x. And then you see that it's every single term it goes through, so it's x to the n, and then it's just over n. There's no factorial, which is nice. And so when you're doing that, you just from 0 to infinity, yeah. And this is just from negative 1 to x to 1. And so that's your, for those numbers. All right, so that's basically all of maclaurin and Taylor series. Thanks for watching. Here's my puppy again. That's Fitz.
And then Kirby is over there, lying on the couch. Yep, thanks.